Hello. In this series of sessions, we'll be talking mainly about CPU scheduling in operating systems. And also we'll be addressing in various different short sessions information about each of the algorithm in detail. Now, in previous session, we talked about different terminologies used in the CPU scheduling. So let us move further and really discuss how exactly this CPU scheduling things are. So when we define CPU scheduling is said to be the process by which your operating system decides which process from the ready queue will be assigned to the CPU for execution, definitely. Now, the scheduling mechanism is very critical to ensure efficient CPU utilization. Also, we have to minimize the process waiting time and optimizing the performance, overall system performance. Now, in multi-programming environment, multiple processes compete for CPU time. And CPU scheduler is responsible to select a process and allocates the CPU time based on scheduling policy and algorithms. Now, effective scheduling enhances the performance by ensuring that no process is left waiting infinitely or indefinitely. And the system resources should be utilized in an efficient manner. Now, when we do talk about objectives of the CPU scheduling, the main goal or main objectives, let us say these are the five, but we cannot only consider these five. There can be lot more, but let us address these five one by one. Now, when we say that one of the objective is maximizing the CPU utilization, ultimately we have to ensure that the CPU remains busy as much as possible, avoiding the idle time. Further, the scheduler should aim to minimize the time when CPU is remaining idle. So as a whole, one can say that we have to ensure that CPU is not idle and always executing the process when you're possible. Second objective is minimizing the waiting time. Now, waiting time is the duration we know a process spends in the ready queue before getting the CPU time. Generally, a well-optimized scheduling algorithm reduces the average waiting time of a process. And that's the reason we are saying that the objective is to reduce the amount of time a process waits in the ready queue before execution. Now, third objective is minimizing the response time. Response time is taken from the process submission to the first response. Now, we have to consider that it is not completion. Important for, and this is very, very important for interactive systems where users expect quick response. It could be like, for example, real-time applications, web servers, and so on. So overall, what we have to address is we have to see that like whenever CPU scheduling is to be or CPU scheduler is to be used, we have to see that we should minimize the response time by improving system responsiveness, mainly for interactive processes. And to achieve this, we have to reduce the delay before a process starts execution. Next objective is minimizing the turnaround time. Turnaround time is the total time taken from process submission to process completion, as we already know this. And we have to also understand here that it includes waiting time, execution time, and any delays in the system. And that's why we have to see how can we decrease the total time taken for a process to complete from arrival to termination. And this could be one of the important objective with respect to the CPU scheduling. Next is ensuring fairness. Now, the scheduler should see that each process gets a fair chance to execute. And it should prevent starvation where some processes are delayed due to other high priority processes. And that's why we are saying that every process should get a fair chance of CPU time. Even one can say like one of the objective probably can be optimizing the throughput. And as we know, throughput refers to the number of processes completed per unit time. And a very good scheduling algorithm definitely increases the throughput by efficiently handling the multiple processes. Now, when the CPU schedulers are designed or defined, there are said to be two types of CPU scheduling. Primitive scheduling, like the CPU can be taken away from a running process before it finishes, and non-primitive scheduling. Once a process starts execution, it cannot be interrupted until it completes or enters in the waiting state. So these are the basic types of CPU scheduling algorithm, and we will be seeing algorithms which would be categorized into these two types only. So first is primitive scheduling. Now let us see some more details about primitive scheduling. The CPU can switch from one process to another before the current process completes execution. A running process can be interrupted and moved back to the ready queue if some high priority process comes. And that's why we are saying operating system can interrupt a running process if a high priority process arrives. And like we are this primitive scheduling ensures better responsiveness in real time and interactive systems. Context switching occurs more frequently here, and which can introduce some overhead, definitely. So, like examples perspective, uh, time sharing systems where multiple users are sharing the CPU, one can see this primitive scheduling is used there. Even RTOS real-time operating system, where urgent task must be executed immediately. In such cases, this primitive scheduling is always good. Now, advantages of primitive scheduling ensures better CPU utilization. First important thing, by preventing long processes from monopolizing the CPU time. Improves response time for interactive processes and real-time process. And high priority task execute sooner, and probably it is kind of a basic goal of real-time processing. Now disadvantages, like there is increase in context switching, and that is an overhead which can slow down the system performance. Sometimes one may see that this primitive scheduling can lead to starvation for lower priority processes. If high priority process keep arriving, and it is very like complex to implement because it requires careful handling of interrupts and process states. So this is about primitive scheduling. The another type is non-preemptive scheduling. Once a process starts execution, it runs until it completes or voluntarily enters in a waiting state. So once a CPU is assigned to a process, we cannot take it away until the process finishes. And it is very simple to implement as no force context switching occurs. But again, it is like when we say that it is simpler, but it can lead to issues like convoy effect, where long processes delay shorter ones. Advantage perspective, it is very simple and easy to implement. Lower overhead since no context switching occurs due to preemption. Easier to implement and manage, like very simple to implement. Disadvantage perspective can lead to poor response times for interactive processes. Like as we stated that it may cause convoy effect where shorter processes have to wait for longer ones to finish first. And this can decrease the CPU utilization because idle time can increase if a process gets stuck. A use case perspective or implementation perspective, like one can see implementation of non-preemptive in simple embedded systems with assumption that there is a predictable workload. Now, when we talk about batch operating systems or batch processing systems, where all jobs are running for completion, this also can be one of the better approach. Now here, like while schedulers are designed or defined, or algorithms are designed or defined, there can be different criteria used. Like for example, one aspect may be CPU utilization. How much time CPU is busy. We are already addressed these terminologies, but as on a revision perspective, let us address them. Throughput, as we stated, number of processes completed per unit time. Even like we have to see that how exactly context switching is controlled. And there can be like multiple algorithms. In coming sessions, we'll be talking about one algorithm each in every time. Where would be computing, would be given set of processes. We'll be talking about an example perspective. We'll try to compute turnaround time, average turnaround time, waiting time, average waiting time, and so on. Thank you.